welcome to this problem walkthrough. In today's session, we will explore problem number 1643, titled KTH Smallest Instructions. We'll break down the problem, analyze the approaches, and provide an efficient solution. Let's dive in. In this problem, you are given an m by n grid, and you start at the top left corner, which is coordinate 0, 0. Your goal is to reach the bottom right corner, located at m, n. At each step, you can only move either down or right. The sequence of these moves is represented by a string of length m plus n, where h corresponds to a move to the right, or a horizontal movement, and v corresponds to a move down, or a vertical movement. The task is to write a function that returns the KTH lexicographically smallest sequence of these moves among all valid sequences that take you from the start position to the destination. The input will include the destination, represented as an array, R, C, where R is the number of vertical moves required and C is the number of horizontal moves. Additionally, you are given an integer k, which specifies the one-based index of the sequence to return. The output should be the KTH smallest sequence as a string. To understand this better, let's look at some examples. In the first example, the destination is 2, 3, meaning you need 2 vertical moves and 3 horizontal moves to reach the bottom right corner. The input also specifies k equals 3, so we need the third lexicographically smallest sequence of moves. First, all valid sequences are generated and sorted in lexicographical order. These sequences are HHVVH, HHVHV, HHVHH, and so on. The third sequence in this sorted list is HHVHV, and that is the output for this example. This demonstrates how the problem requires generating sequences in lexicographical order and selecting the KTH one. Continuing with the first example, the full list of valid sequences is as follows: HHVVH, HHVHV, HHVHH, HVHHV, HVHVH, HVVHH, VHHHV, VHHVH, VHVHH, and finally VVHHH. From this sorted list, the third sequence is HHVHV. Now, in the second example, the destination is 2, 2, meaning you need 2 vertical moves and 2 horizontal moves to complete the path. The input specifies k equals 6, so we are looking for the sixth lexicographically smallest sequence. Sorting all valid sequences, we get HHVV, HVHV, HVVH, VHHV, VHVH, and VVHH. The sixth sequence in this list is VVHH, so that is the output for the second example. In the second example, we saw how to determine the KTH smallest sequence by sorting all valid sequences. Now, let's consider the third example. Here, the destination is 1, 4, meaning there is 1 vertical move and 4 horizontal moves required. The input specifies k equals 4, which means we need the fourth lexicographically smallest sequence. Generating and sorting all valid sequences, we get HHHHV, HHVHH, HVHHH, and HHHVH. Among these, the fourth sequence is HHHVH, which is the output. This example highlights how the method applies even when the number of moves is heavily skewed toward one direction. The explanation for the third example follows the same principle of sorting all valid sequences in lexicographical order. With 1 vertical move and 4 horizontal moves, the total number of valid sequences is relatively small, making it straightforward to determine the KTH smallest sequence. However, when the grid size increases, the number of sequences grows rapidly, and an efficient approach is essential to compute the result without explicitly generating all possibilities. The problem also includes constraints to ensure that k is always valid for the given inputs. Specifically, the value of k is guaranteed to be within the range of possible sequences, given by the formula, r plus c / r * c. Finally, let's discuss some edge cases. When there are minimal moves required, such as r equals 1 and c equals 1, there are only 2 valid sequences, hv and vh. The output will depend on the value of k. For cases where all moves are in one direction, such as r equals 0 and c equals 10, the result will always be a string of 10 h's. Similarly, if r equals 10 and c equals 0, the result will be a string of 10 v's. For maximum constraints, like when r equals 15 and c equals 15, the function must efficiently compute the KTH sequence without explicitly generating all possibilities, as the total number of sequences can be extremely large. These edge cases emphasize the importance of handling both small and large inputs effectively. To start, let's consider the brute force approach, where we aim to generate all possible paths from the top left to the bottom right of the grid. The intuition here is that each path can be represented as a sequence of H and V moves. For example, if there are M vertical moves and N horizontal moves, we generate all combinations of these moves, then sort them lexicographically, and finally select the kth smallest path. This can be implemented using backtracking to explore all valid sequences of length M plus N. However, this approach quickly becomes inefficient for larger grids due to the exponential growth in the number of paths. The time complexity involves generating all possible paths, which is proportional to the binomial coefficient M plus N / M * N, and sorting these paths adds further overhead. Additionally, the space required to store all the paths makes this method impractical for larger inputs. While straightforward, it's clear that this approach isn't scalable for large grids or high values of M and N. Now, let's look at the optimized approach, which leverages mathematical combinations and avoids generating all paths. The key insight here is that the kth smallest path can be constructed step by step by calculating how many paths begin with a particular move. At each step, we determine the number of paths that would start with an H. This is done using the combination formula C, M plus N1 in 1, which calculates the number of ways to arrange the remaining moves if H is chosen next. If K is less than or equal to this value, the next move is H. Otherwise, the next move is V, and we subtract the number of paths starting with H from K to update our target. We continue this process until the entire path is constructed. This approach is highly efficient, requiring only O, M plus N, time to calculate the path, and uses constant additional space. While it does require a solid understanding of combinatorics and careful implementation, its efficiency makes it highly suitable for this problem. Another alternative is the dynamic programming approach, which focuses on pre-computing the number of paths from each cell to the bottom right corner. This involves creating a DP table where DP, I, J, represents the number of paths from cell, I, J, to the destination. Once the table is built, it can be used to dynamically decide whether the next move should be H or V. For example, at any point, if the number of paths when moving H is greater than or equal to K, we choose H. Otherwise, we choose V and adjust K accordingly. This approach provides a structured way to solve the problem and is particularly useful for understanding the distribution of paths across the grid. However, it has a higher space complexity since the DP table requires O, M * N storage. While systematic, the added memory overhead makes it less efficient compared to the optimized combinatorial approach. Ultimately, we chose the optimized approach based on combinatorial path construction as the most efficient solution. By directly leveraging the mathematics of combinations, we can construct the kth smallest path without generating or storing all possible paths. This method is not only fast, with a linear time complexity relative to the path length, but also space efficient, requiring no additional data structures. One key insight that made this approach especially powerful was recognizing that the number of paths starting with H could be calculated directly, allowing us to avoid unnecessary computations. Compared to the alternatives, the brute force approach, while simple, is computationally infeasible for large grids, and the dynamic programming solution, although systematic, incurs significant space overhead. The combinatorial approach strikes the perfect balance between scalability and efficiency, making it the most practical choice for solving the kth smallest instructions problem, especially for larger inputs. To solve the problem of finding the kth lexicographically smallest path in an M by N grid, we need to understand the structure of the paths. Each path consists of exactly M horizontal moves, represented as H, and N vertical moves, represented as V. These paths start at the top left corner and end at the bottom right corner of the grid. A brute force method would involve generating all possible paths and then sorting them to find the kth one, but this is extremely inefficient because the number of paths is given by the binomial coefficient C, M plus N each M. Instead, we use a combinatorial approach. By leveraging the properties of lexicographic order and binomial coefficients, we can directly construct the desired path without generating all possibilities, making this method computationally efficient. The algorithm constructs the path iteratively. We start with an empty string and decide at each step whether to append h or v. To make this decision, we calculate how many paths start with h versus v using the binomial coefficient. If there are h_m horizontal moves and v_m vertical moves remaining, the number of paths beginning with h is given by c, h_m plus v_m1, h_m1. If the count of these paths is greater than or equal to k, we append h to the path and decrement h_m. Otherwise, we append v, adjust k by subtracting the number of paths starting with h, and decrement v_m. This process is repeated until all moves have been used, ensuring the path is constructed correctly step by step. The use of binomial coefficients is central to this algorithm because it allows us to calculate the number of valid paths without explicitly generating them. By prioritizing h over v lexicographically, we can dynamically compute and compare the number of possible paths at each step, ensuring we always make the correct decision for the kth smallest path. This approach is highly efficient compared to a brute force method, which would involve generating all paths, taking exponential time and space. Here, the combinatorial approach reduces the complexity to linear time and constant space. For edge cases, when k equals 1, the path is simply mh's followed by nv's, and when k is the total number of paths, the path is nv's followed by mh's. To implement this algorithm, we use simple and efficient data structures. First, a string is used to iteratively build the resulting path by appending one move at a time. Second, integers are used to track the remaining counts of horizontal and vertical moves, h_m and v_m respectively. Additionally, binomial coefficients are calculated dynamically using integer arithmetic instead of pre-computing factorials, which avoids unnecessary computations and the risk of integer overflow. These minimal data structures keep the algorithm not only efficient but also straightforward to implement. The key operations in this algorithm revolve around calculating binomial coefficients and making dynamic decisions based on their values. Instead of calculating factorials directly, we compute the coefficients iteratively using the relationship c, a, b, equals c, a1, b1, *b, which avoids inefficiencies and allows precise calculations. Each step involves comparing k with the number of paths starting with h to decide whether to append h or v to the path, while updating k and the remaining move counts accordingly. This ensures the algorithm runs in m plus n time, as it calculates at most m plus n coefficients. The space complexity is 1, because the algorithm only uses a few variables and does not require additional storage, making it highly optimized for the problem. This Python implementation efficiently solves LeetCode problem 1643, kth smallest instructions, by leveraging combinatorics to avoid generating all possible paths. The goal is to find the kth lexicographically smallest path from the top left corner to the bottom right corner of a grid, given the number of horizontal, h, and vertical, v, moves needed. ###line by line explanation. 1. Import comb from math library. The comb function calculates binomial coefficients, crucial for determining how many paths start with a specific move. 2. Define the kth smallest path function. This function takes the destination, a pair of integers, and the rank k of the desired path. 3. Extract rows and columns. Rows represents the required vertical moves, v, and cols represents horizontal moves, h. 4. Initialize result list. This will store the path as we construct it step by step. 5. Iterate through the total number of moves. For each decision point, choose h or v. 6. Check remaining horizontal moves, cols. If horizontal moves are greater than 0, determine the number of valid paths starting with h using the binomial coefficient comb, rows plus cols 1, cols 1. 7. Compare k to count_h. If k is less than or equal to the number of paths starting with h, append h to result and decrement cols. Otherwise, append v, subtract count_h from k, and decrement rows. 8. Handle remaining vertical moves. If no horizontal moves remain, append all remaining v moves to result and break the loop. 9. Join and return the result. Convert the result list to a string and return it. ###key insights. This approach avoids generating all possible paths using combinatorics to calculate the number of paths dynamically. This keeps the time complexity manageable, approximately m plus n, where m and n are the grid dimensions. By iteratively updating k and choosing the next move strategically, the algorithm efficiently constructs the desired path without sorting or excessive computation. This makes it suitable for large inputs, adhering to competitive programming constraints. Here, we start implementing the solution for finding the kth smallest path using Java. First, we import the necessary library for handling large numbers, specifically big integer, which will be useful later for computing combinations. In the kth smallest path method, we take two inputs, the destination array representing the target coordinates and the integer k denoting the kth smallest path we need to find. We then initialize rows and calls to represent the number of vertical and horizontal steps required to reach the target. A string builder object, result, is used to build the path step by step efficiently. The main logic involves iterating through the total number of moves, which is the sum of rows and calls. For each iteration, we first check if horizontal moves, represented by h, are still possible. Using the helper method combination, we calculate the number of paths that start with h, denoted as count_h. If k is less than or equal to count_h, it means the kth smallest path starts with h, so we append h to the result and decrement the count of horizontal moves. Otherwise, the path must start with a vertical move, v. In this case, we append v, adjust k by subtracting count_h as those paths starting with h are skipped and reduce the vertical move count. This process continues until there are no more horizontal moves left. When no horizontal moves remain, the loop appends all remaining vertical moves, represented by v, to the result. Finally, the method returns the constructed path as a string. The helper method combination is crucial for calculating the number of ways to arrange the remaining horizontal and vertical moves. The method takes two parameters, n and k, and returns the number of combinations of choosing k items from a total of n. To handle large numbers, we utilize big integer for both the numerator and denominator. The numerator is calculated by multiplying consecutive integers from n down to nk plus 1, while the denominator is the factorial of k. After computing these, we divide the numerator by the denominator and return the result as an integer. This ensures that the combination calculation is both efficient and accurate, even for larger values of n and k. Together, this implementation effectively constructs the kth smallest path by leveraging combinatorics and efficient string building. Here, we are tasked with finding the third lexicographically smallest path to the destination, 2, 3, which means moving 2 rows down and 3 columns to the right. Starting with the initial state, we have 2 rows, 3 columns, and our k value is 3. The result array is empty at this point. In the first iteration, we calculate the number of paths starting with an h, which is determined using the combination formula. Specifically, com4, 2 equals 6. Since k is less than or equal to this count, we append h to the result, reducing the column count to 2. Moving forward, we calculate count_h for the updated state as com3, 1, which gives us 3. Again, k is less than or equal to this count, so we append another h and reduce the columns to 1. In the third iteration, we calculate count_h as com2, 0, which equals 1. This time, k is greater than count_h, so we append v instead, signaling a move downward. After appending v, we update k to 2 by subtracting count_h, reduce the rows to 1, and continue with the result now as v. For the fourth iteration, we calculate count_h for the updated state as com1, 0, which equals 1. Here, k is greater than count_h, so we append another v to the result, reduce the rows to 0, and update k to 1. In the final iteration, since there are no rows left, we append h to complete the path. The final result is h, which corresponds to the output hhvvh. This path is the third lexicographically smallest path to the destination. In this example, we are finding the second lexicographically smallest path to the destination, 1, 2, which involves moving 1 row down and 2 columns to the right. Starting with our initial state, we have 1 row, 2 columns, k equals 2, and the result array is empty. For the first iteration, we calculate count_h as com2, 1, which equals 2. Since k is less than or equal to this count, we append h to the result and reduce the columns to 1. Moving on to the second iteration, we calculate count_h as com1, 0, which equals 1. Here, k is greater than count underscore h, so we append v to the result, reduce the rows to 0, and update k to 1. Finally, since no rows remain, we append h to complete the path, resulting in hvh. This corresponds to the output hvh, which is the second smallest path. For the third example, the task is to determine the fifth lexicographically smallest path to the destination, 3, 2, which involves moving 3 rows down and 2 columns to the right. Beginning with the initial state, we have 3 rows, 2 columns, k equals 5, and the result array starts empty. In the first iteration, we calculate count underscore h as comb, 4, 1, which equals 4. Since k is greater than this count, we append v to the result, reduce the rows to 2, and update k to 1 by subtracting count underscore h. Next, in the second iteration, we calculate count underscore h as comb, 3, 1, which equals 3. This time, k is less than or equal to the count, so we append h to the result and reduce the columns to 1. With the columns now reduced to 1, we calculate count underscore h as comb, 2, 0, which equals 1. Since k is less than or equal to this count, we append another h to the result, reducing the columns to 0. At this point, there are no more columns left, so we append v twice to account for the remaining rows. The final result becomes v, h, h, v, v, which corresponds to the output vhhvv. This is the fifth lexicographically smallest path to the destination. To analyze the time complexity of our solution, we need to break it down into 2 key components: the combination calculation and the number of iterations in the loop. First, the comb function is called during each iteration of the loop to compute the number of paths starting with h. The runtime of this function depends on the smaller of its 2 inputs, making it approximately O, min, A, B, where A is the total number of moves remaining and B is the horizontal moves left. In our specific case, this translates to O, min, rows plus calls 1, calls 1. Next, the loop itself runs for exactly rows plus calls iterations, as we are constructing a path with this total number of moves. When we combine these factors, the time complexity of the solution becomes O, rows plus calls, asterisk min, rows plus calls, calls, since the comb function is called once per iteration of the loop. This gives us an efficient way to determine the kth smallest path without generating all possible paths explicitly. Now let's discuss the space complexity. The solution uses very minimal additional memory during its execution. First, the comb function does not require significant auxiliary space. It only uses a few variables for intermediate computations, so its space contribution is O1. Next, we have the result list, which stores the final path as a sequence of rows plus calls characters. This requires O, rows plus calls, space, as the length of the path is equal to the total number of moves. Lastly, the input variables themselves, such as destination and k, occupy constant space, O1. When we combine all these factors, the overall space complexity is dominated by the storage of the result list, resulting in O, rows plus calls. This makes the solution efficient in terms of memory usage as well. When we evaluate the best, average, and worst cases for this solution, we find that they are identical in terms of time and space complexity. This is because the number of iterations in the loop is always equal to rows plus calls, and the comb function is called during each iteration regardless of the specific input values. Therefore, the time complexity remains O, rows plus calls, asterisk min, rows plus calls, calls, and the space complexity remains O, rows plus calls, across all cases. Comparing this to a brute force approach, the efficiency of our solution becomes even more apparent. A brute force method would involve generating all possible paths, sorting them, and choosing the kth smallest. This would require O, rows plus calls, / rows. Asterisk calls, time just to generate the paths, and additional time for sorting. Such an approach would be computationally infeasible for large inputs because of factorial growth. Furthermore, the space required to store all paths would also grow exponentially. By leveraging combinatorics, our solution avoids generating all paths and directly computes the kth smallest path, making it far more efficient in both time and space. Finally, let's solidify our understanding of the time and space complexity with a mathematical proof. The most significant contributor to the time complexity is the comb function, which calculates binomial coefficients. Each call to comb takes O, min, rows plus calls, calls, and since it is called once per loop iteration, the total time complexity becomes O, rows plus calls, *min, rows plus cols. This aligns with our earlier analysis. For space complexity, the primary factor is the result list, which grows linearly with the total number of moves, rows plus cols. This results in a space complexity of O, rows plus cols. Together, these insights confirm that our solution is both time and space efficient, especially when compared to the brute force approach, making it well suited for solving this problem for larger inputs. When solving this problem, there are a few common mistakes to watch out for. First, many confuse permutations with combinations. Remember, permutations consider the order of all elements, while combinations focus on selecting elements without regard to order. For our problem, the task is to respect the constraints of the grid, which means sticking to the required number of horizontal and vertical moves. Generating all possible sequences without considering these constraints leads to inefficient or incorrect solutions. Another issue is mishandling duplicates. For example, paths like HHVV might be counted multiple times if we aren't careful. The key is to use methods like backtracking or combinatorics to systematically generate unique paths. Lastly, edge cases such as 1xn or nx1 grids, where there's only one valid path, are often overlooked. These trivial configurations should be tested and handled separately to ensure reliability of the solution. Another pitfall involves inefficient brute force approaches. Generating all possible paths and then sorting them to find the kth smallest path is computationally expensive, especially for larger grids. This method, which has a factorial time complexity, might work for very small grids but quickly becomes impractical. Instead, we can use combinatorial mathematics or optimized backtracking techniques to calculate the kth path directly. Additionally, off-by-one errors are a frequent source of mistakes, particularly when indexing the kth path. This often arises from confusion between zero-based and one-based indexing. Careful attention to the problem's description and consistent indexing adjustments can help avoid this issue. Understanding the underlying patterns in grid-based problems is vital for tackling variations in this type of question. Many of these problems can be solved using approaches like dynamic programming, backtracking, or combinatorics. Recognizing which method aligns with the problem's requirements is often the key to solving it efficiently. For kth smallest path problems specifically, sorting the paths is rarely optimal. Instead, leveraging lexicographic order or combinatorial properties allows for direct computation of the result. Interviewers may also present follow-up questions that extend the problem. For instance, they might ask how to handle higher dimensional grids, such as 3D, or introduce obstacles within the grid. Lastly, clear communication during interviews is essential. Be prepared to explain the trade-offs between brute force, dynamic programming, and combinatorial methods while justifying your chosen approach. To deepen your understanding of this problem, it's helpful to explore related problems on LeetCode. For example, LeetCode 62, Unique Paths, asks you to find the total number of unique paths in an MXN grid, which builds foundational skills in grid traversal. LeetCode 31, Next Permutation, is useful for mastering lexicographic ordering, a key concept in combinatorics. LeetCode 119, Pascal's Triangle 2, helps solidify your understanding of combinatorics and binomial coefficients, both of which are central to calculating paths efficiently. Finally, LeetCode 980, Unique Paths 3, introduces variations with obstacles and additional constraints, pushing you to adapt your approach to more complex scenarios. There are several alternative approaches to solving this problem, each with unique trade-offs. Dynamic programming is efficient for counting the total number of paths in a grid, with a time complexity of O(m*n) for MXN grid dimensions. However, it is less intuitive when it comes to directly generating the kth smallest path. Backtracking with pruning is another option. It's relatively simple to implement and can be adapted for variations like handling obstacles, but it may not scale well for larger grids due to its worst-case complexity of O(2)m+n). Pruning, however, can significantly reduce this. The optimal approach is using combinatorics to calculate the kth path directly. This method relies on binomial coefficients and lexicographic order, offering time complexity of O(m+n) for path generation. While highly efficient, it does require a strong grasp of combinatorial concepts. Great job! We've successfully solved problem number 1643, KTH smallest instructions. Today, we learned how to apply combinatorics to optimize the solution and avoid brute force. Remember to practice problems like this to strengthen your problem-solving skills. Thank you for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!